Good afternoon, and welcome to another video in the series on data structures. In the last video we had a first look at bitsets, and we implemented a simple way of testing out whether a specific character was a vowel or not. And we pretty much did that by hard coding our vowels for our set, which it's quite lovely, but also pretty pointless because most of the time we have a dynamic set of information. But before we get going and pick up a more useful set, let's reflect a little bit about the algorithmic complexity that our operations on the set had. And if you look at earlier videos, we discussed these things by using the big O notation. Now let's have a quick look at what all these operations are. And if you remember, there were three specific operations that we've implemented, which was the set, the unset, and the isset operations. And all three of these operations, the algorithmic complexity was, well, we take this number and we will instantly figure out where in our bit set this is, and we flip the bit. So no matter how many elements we have in our set, the operation is always going to be one specific thing to do. So that makes it a big O notation of O(n), or rather, sorry, O1 even, which is pretty good. But as I said, hard coding vowels is kind of pointless. What we really want to do is we want to figure out, in a different way of what makes sense. Now, as an example, what I'd like to have a look at is I'll create a file that we can read, and we figure out, say, all the Fibonacci sequence numbers under 100. I mean, it's not the most useful thing, but let's create a file that contains all of these. And let me show you that. So just opening a different file, it's called fibon.txt, not particularly very interesting, and the numbers, the sequence in the Fibonacci sequence, it starts with a 1, and then a 2, and then each subsequent number is the sum of the two just above it. So 1 plus 2 makes 3, 2 plus 3 makes 5, 5 plus 3 makes 8, we get 30, 21, 34, 55, and then 78. So this is 9 numbers. Well, technically they're 10 because 1 should be counted twice, but this is not something we can do, right? So we have 9 numbers for our set, and we're only looking at all the numbers under 100. So that is 9 out of 100. So how do we get that into the set? Well, on the right hand side here, we still have our program from the previous time, and we just need to modify it a little bit by changing some of the functions in there. So first of all, instead of going to look for a specific letter, we're not going to look for a letter, but we're going to look for a number. And that does not much to the usage thing, except that, to be precise, we should give it a number, right? Now, our set isn't going to be called vowels anymore. We're renaming that to Fibon, because I never know how to spell Fibonacci, to be honest. Fibon, and then we will re-implement our set loading as well. So in the future, our number that we're going to look at is now not just the first character, but it's a whole argument. So our car letter here is going to have to be car star for a string, a null terminated string, but it contains the number that we're going to look for, see whether it is part of our set. And we do then the same. Instead of is vowel, we do is Fibon. Of course, it's not going to fit on the screen now. Fibon, and then we have our number. And then at the end, we free up our set again. So this isn't particularly interesting, of course. The interesting thing is that, well, how big are we going to make our set? well, we need to make the set as big as we know it is going to be, and the premise of this was that we're looking at all the numbers under 100, and that of course makes the set size 100. If the number 100 would also have been a Fibonacci number, we would just discount that. And of course, when we load this, we need to keep track of this. Now, we want to configure our set no longer from just hard coding them, although we can, of course, do hard code the numbers that we have here. Here, we're doing the set. What I want to do actually is I want to read this information from a file, and you'll find out in a future example why I want to do that. So instead of reading the sets, what I want to do is I want to read from a file, and the file name that we're going to use is the one I've just created here. It's called fibon.txt. Now, how do you do file handling in C? Well, there's two different ways of doing that. There's a very low-level interface, which is you use open to work directly with files, and that is kind of a really cumbersome interface, because you need to take care of buffering yourself and so on and so on. But there's a slightly higher level interface in C, which is the file pointer type. And files in this you can open with a function called fopen. You give it the name of the file, and then you need to tell it which mode you want to open this in. Now, modes are things such as do I want to open it for reading or writing? And if I'm reading it, if I'm writing it, do I want to write it in append mode or not? But in this case, we only want to read from a file, so you specified it by this character pointer called R. Now, as always, you always need to check the return values of functions, and if you don't do that, bad things can happen. So what we're going to do is that if the file isn't opened correctly, and we'll test that by misspelling the name in a moment, we want to show an error, which we say, for example, can't open file, and then we can, well, probably exit the function, right? And that's it. Now you see that what I do here is actually I do the if and then the negative, so that I can immediately, if something goes wrong, jump out of this whole function altogether, and whether you do that with exit or not, that doesn't particularly matter. But it means that the top level, the first indentation, so to say, always has the code, and all the exit statements are always away from that, and I find that just a nice way of doing things. Now, if we have done this, we need to, of course, read all the lines in the file. And the way of doing that is you can loop over the file as long as the end of the file has not been reached. And you can test that with FAOF, or FEOF, which stands for end of file. And as long as we don't have an end of file, what we can do is we can read from the file. We need to read into a specific buffer, or rather, I cannot now not remember the function prototype, so that's where we have the man pages, right? Man fgets, nope, helps if I spell correctly. So what does it take? It reads something out, it reads it into a buffer, and then you need to specify the size and then the file string. Now, interestingly, it returns a pointer to the buffer that it is read from. Why it does do that, I don't know, but if you want to figure out what the return value is, it's usually further down in the man page. It says fget says returns as on success and null on an error, or when the end of file occurs, while no characters have been read. So actually we don't have to use the FEOF. We can basically do the whole do while here, and if our read number, so this is our buffer, this is our length, we'll fill in the length in a moment, and this is our file. Do this, we can do this as long as read number is actually set. of course, we need to define read number. Nope, read number. So that can be our simple loop, but we also need to specify what we're going to read it in. Now, at the moment, we know how big the strings are that we're going to read, which is only going to be 2 characters for the number, plus the new line at the end, plus an extra character for the null termination. So even to read 2 numbers with a new line attached to it, you end up having to create a buffer that's at least 4 big. But I'm going to be a little bit better here and just make it a little bit larger. Let's say make it 256 because of examples that are going to follow later on. So yes, we specify the buffer because it wants a car pointer. That works because we specify this as a string length. So just filling in buffer works just fine. And then the length of the buffer is we can do size of buffer. Okay. Oh, sorry, making this a bit wider so that we can fit everything on the side. So when we read this, if the read number is actually a number, we can do just at the moment we echo this number and we specify that with the %d, and d, no, we can't do that yet because we haven't converted the number yet. The %s means in this position show a string, and we're just going to show the string. And this will basically loop as long as we have a number, and then at the end what we can do is we need to close the file, and then we are pretty much done reading the file. So this is not that hard to do. Let's, however, figure out whether this actually compiles. And I forgot to prepare which screen that was. But here we go. So if I type make, let's see what happens. I still have a few errors because I don't know how to do dual while loops anymore. Of course, that needs to have the while there. If we now run this, we still have one more. We have an error of the isFibN function, which we haven't implemented yet, so that makes sense. In this case, we just specified like this, and of course we now have a character pointer in there, which was our number, and then we need to convert that number to an integer number, and there's a function for that. I don't like doing it like this, but for now this is a quick shortcut. I don't like having the I in front of number because we already have the number string. I think this makes more sense because it is more descriptive of what we're actually doing. Of course, I don't doing anything with number yet, but we just want to, at the moment, compile this and see whether we can read the file. So this compiles now. If we now run this, we get usage test number. Fine, that makes sense. We just do 8. Doesn't matter what we do. But if we run this, we'll see what it shows out, right? It shows all the elements that we have found in our file, and it shows this information on the screen, except that, of course, the new line is still there, which is kind of annoying. However, the more important thing is that although we have read this number now, they are all strings. And a string you can't, as in some language, you can't simply change into a number by just telling it it's a number. There's a set of functions for this. And these are, for example, A to I. Opening the man page again just to show you what these functions can do. So there's different variants of it, and that depend a little bit on what sort of data type you're going to want to convert it into. At the moment, we only pretty much want to care just about integer numbers, not long numbers. We don't really need a data range. So we can simply use A to I, and then we pass in our string. So let's convert our reading function to do just that. And yeah, the return value is going to be either null on error or the number that we're looking for. So we do need to test again for the result here, whether it's accurate or not. So we have our red number here. Again, let me change that to number string. I like being consistent with these things. So we have DOM number string here. If number string is empty, no, number string. If it's number string, then we need to do some more logic here. And what we want to do is pretty much, we want to, our fib number needs to be a to I that we've just done, and then we can fill in a number string. And then instead of displaying this information as a string, we want to show this as a number. And we therefore have to change our %s to a %d, otherwise it would show the wrong data type, and then you will get a crash. So basically we've just converted this from a string into a number, which is what we need to do. So run make again. Again, I made a typo here because I didn't update all of my variables. Let me run it once more. Everything fine. We run test. It will show us our usage error because we haven't given the number yet. We do 8. And now, as you can see, we get the full numbers without either the new line, because a to I will just abort the first character it can't find and then show our number. Now, that's great. That works. Let's remove or move our fib function to F for a moment to see what happens if we can't read a file. And it handily says it can't open a file, so we have covered that. Fibon.txt. So that works. What happens if we put in a line that is just say letters? No, that's numbers. I said letters. What is the output now if we run the program? It shows one with 0 in there, so we do need to take care of that, right? If the number is 0, we don't want to display it or add it to our set. So yeah, we need to check for that. If not fibon, so this is actually nicer to do here, right? If our number is either smaller than 1 or larger than or equal to 100, then we don't want to do anything and we just want to go to the next iteration in our loop, and we do that with continue. So if the number is now too large or not a number, so for good measure, I will alter the next Fibonacci number in there as well, which is 133 in a different order. Run this again. And yeah, of course, now they're still in here, but we don't want that because we've just changed our code. And now again, it discards all the numbers that we don't want. Now, of course, we know what the numbers are, so we can simply remove that. Well, the only thing that we haven't implemented now yet is to add those elements to the set. So we simply implement that. So the name of our set is, what was it? Is simply called sets, perhaps not the best number. And then we say fibon number. So that takes care now of the configuration of our set. Now the only thing we need to do to make sure that we can check for this is we need to also do the A to I conversion here. And we'll do that by rename our arguments here. Again, just to be consistent. And then we do need to convert that to our Fibonacci number, which is A to I again. We do our number string, and then we can simply add that to our set here. And then that should do our tests. Now we don't make, oh, I get an error here. It says passing number 2 of isFib makes pointer from integer without a cause. Of course that makes sense, because if we look to the isFib number, we now pass in an integer instead of a string, so we don't need all of this. It just already takes care of accepting a integer number. So there we go. Okay, let's run make again. And now let's see if our tool works. So if we give the number 3, it gives us the Fibonacci number. Yes, excellent. What if we do 77? It says no, and that is what we expect here, right? Because we have all those numbers here. What about if we say 78? Yeah, that works. What about if we do 800,000, or that's not 800,000, 800,123? What happens if we do this? It gets no. But remember that our set is only 100 numbers long. So if we would actually debug this and figure out with Valgrind, our memory debugging and testing tool, it should actually warn us that we're trying to read information on the outside of our set. And if you run this, it will actually tell you to do so. So interestingly, it says it's an invalid read of size 1 on set is set. But it says it's 95 bytes inside a block of size 147 to read. Now that doesn't make a lot of sense, right? I mean, but if you look at it, it's like a deallocate for a file pointer, which has nothing to do with our code whatsoever. So sometimes the warnings that Valgrind gives you don't make a lot of sense. If you would have run this with a number that is much closer, like saying 123, which is only 23 of our set, our error message would be a lot better, right? Because it now says it's 2 bytes after a block of size 13 allocated. And 13 makes sense because 13 times 8 is 104, right? And 104 is sort of what you would expect if you want to create a set with the size 100. You need a few extra bits to make up a full byte, which makes 13 bytes. So there we go. We do need to test for that because you always need to check for your preconditions. And again, we need to do that by only calling isFubin for the right amount. However, it is much nicer to actually do that in the set itself because we know how large it is, right? So what we can do here, if the number is larger than what we have in the set, and I can't remember the name of the property anymore, is the size. Is it the size? I think so. Or is the size the amount of bytes that we have? I don't think so. I think it's the amount of bits that we can set in our set. Yeah, it's the amount of bits that we set. So yes, we can simply see if our number is larger or equal to our set size, because this is 0 index, it goes from 0 to 99, not 0 to 100. We basically need to say that the number is too large for our set with size S. I'm always a big fan of being very precise with error messages. Error messages in such a way that you clearly know what's wrong and what you can do about it. So in this case, we say what our number is, what we would expect it, and then we can simply exit the function or the whole program. You can do that, that's a choice, or what we can do is just return 0. That depends how you want to structure your program, how to handle errors, for example. But yes, let's compile this again, run our program with a 123, and now it says, instead of throwing a memory warnings, it says basically the number 123 is too large for the set with size 100. Alright, so this is a simple implementation of how we can read from a file all those numbers to our set and then test whether these are part of the set. But we do need to have a look at whether it actually makes sense to use a set in the first place here. Now, from our 100 possible values, we actually only use 9 here, right? So maybe there's a much faster way of, if you know there's only so few numbers in here, to instead, for example, use an array, for example, and then just compare these numbers one by one for that to make sense. In general, these discussions about which data type is the best one is going to depend on, for example, the data density. For example, if you have say 7,800 lines of a text, how many elements are in there? Is it only going to be 10? You don't want to keep information for the 7,800 elements. In this case, we can store information for up to 100 elements, but we only really take care of 9. And if the density is that this low, then it might not make sense to use a set. But I guess in this case, because it is such a small thing to do, it actually does make sense. So yes, in this case, we have read all the Fibonacci numbers from a file, and we can check whether a number is part of the set. But it's a very low density set, and in most cases, you would see that sets are going to be a little bit higher. The density is going to be higher. So to illustrate that, I actually have written myself another example file already. No, but I don't remember the name of the file. It's a file called lines. And what this is, it is a file that has letters in it. As we can see here, it says name. Actually, they're names of functions. The names of functions in the file that I've created a while ago. And all the numbers in here are line numbers. So if we open this file, put it the other way around, let me enable the line numbers. Basically, what the file on the left is a description of which lines on the right hand side have code on it as the PHP engine sees it. What the data source is or where it comes from is not important here, but I just wanted to illustrate that sets are actually useful in real life cases, and Xdebug, the debugger tool that I wrote, makes extensive use of this for analyzing whether lines in a PHP file have executable code on it and whether they're executed. It is extensively used for providing code coverage. And in some cases where people that write PHP expect lines of code to be on, might not necessarily be places where there is code. So take, for example, our find redirect method that says there's line of code on 11, 13, and 14. So this is information that came out of a tool called VLD that at some point I will create a video about as well. And that is a tool that basically shows you on which lines the PHP engine sees lines of code. So it says for the function find direct, there's code on line 11, 13, and 14. Okay, how much sense does this actually make? So let me make this a bit wider again. I need to actually enable the wrapping here. Okay, it says there's code on line 11. That makes sort of sense. There's some checks necessary for making sure that the variables are of the right type. There's clearly code on line 13, which is our calling another function, but line 14 is pretty rudimentary, right? And yeah, that is just a way of how PHP does things. There's always an implicit return at the end of every function. That's just how it is. I can't do anything about it. But yeah, basically we have this line. Now, how would we use the definition that we have on the left-hand side here? How would we use that to figure out which functions will have specific lines of codes in them? Well, in order to do something with this, well, we can figure out what we need to do is we need to basically map the line numbers to a function name. That is, of course, a bit trickier to do because a set doesn't really encode a line number to a data structure combination. It only really remembers what is on the specific line. And hence, this is not where a set would be useful. Instead, what would make perhaps more sense is that how do you create this mapping between these numbers and these function names? Now, one thing could be is that we could create a set for every function, and then we can do a lookup against that, and that could work. Or what we can do is implement a different data structure where for each of the line numbers that we have, we remember not just whether it is set or not set, but rather what the specific function number is. And by function number, I mean In this case, main will be the first function, so function number 0, or lambda1 will be function number 1, and so on. And we can create a data structure around that, and then we can map these line numbers very much like a hash function, actually, except that, well, we don't create a hash here because we only need to take care of the numbers, right? And that is something that we can implement. Now, as I mentioned, we can already use a hash for that we've implemented in previous videos. And some implementations of hashes take numbers in a different way. Instead of having to run our hash function on them, it will actually just take the number and just modulo it to fit in the buckets that we have. So that is a way of doing it. Again, both are valid. I don't know which one to implement here. So if you want to shout out in the chat which one we should do, either modify our hash to allow for numbers in a more simpler way, or do we create basically a list of sets so that for each of them we can check whether the function or the line number that we're looking for matches with the set that belongs to that specific function. So with that, I'd like to say thank you for attending today, and we'll be back next week with a video on how you'd combine the hashes with the set, for example, that I've just illustrated. So I'd say thank you very much for attending, and I will see you next week.